Here's something to truly ponder as you settle in, something that expands the mind in a way few other concepts can. Every single star you can see with your naked eye in the night sky, every single one, is a part of our own Milky Way galaxy. That's about 2,500 to 5,000 individual points of light, depending on how dark your sky is. But here's the mind-bending part. Our galaxy contains somewhere between 100 billion and 400 billion stars. Think about that for a moment. You see maybe 5,000, yet there are hundreds of billions more, completely invisible to you without aid, lost in the sheer immensity of our galactic home. Now, let's take that scale and shatter it even further. The Milky Way, this colossal island of stars, gas and dust, is just one galaxy. And within the observable universe, the part we can theoretically see, there are an estimated 2 trillion galaxies. Not 2 trillion stars, but 2 trillion galaxies, each containing hundreds of billions of stars. It's a number so vast it feels less like a quantity and more like a philosophical statement. It's the universe whispering, "You're so much smaller than you can possibly imagine." What does it mean to say the universe is 2 trillion galaxies large? How does our relatively familiar Milky Way, with its comforting band of light across the night sky, fit into that incomprehensible cosmic tapestry? How do we even begin to measure such distances, such colossal structures, and what does it feel like to build a mental model of something so utterly beyond our everyday experience? This isn't just about numbers. It's about understanding the very fabric of existence, about where we stand in the grand cosmic scheme. It's about intellectual fascination that, by its sheer richness, allows the mind to drift into a state of contented wonder. If you're enjoying this journey through science, hit that like button and subscribe so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city and time zone you're watching from. There's something special about knowing this story is reaching people all over the world as we collectively ponder the vastness of space. Let's begin our journey by truly grasping the immensity of our own backyard, our galactic home, the Milky Way. Here's a thought that might seem counterintuitive. Even though we live within the Milky Way, we can't actually see what it looks like from the outside. No human-made probe has ever left our galaxy, nor will one for millions of years. The iconic images you see of spiral galaxies, the majestic arms, the glowing core, those are other galaxies observed from billions of light years away. Our view of our own galaxy is from the inside, like being in a vast forest trying to map its entire extent. And yet, through incredible ingenuity and scientific detective work, we have pieced together a stunning portrait of our home, a portrait that reveals a scale so vast it redefines what big truly means. To understand the Milky Way, we first need to understand what a galaxy is. At its simplest, a galaxy is a gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and an important yet unseen component called dark matter. These components are all held together by their mutual gravitational attraction, forming a distinct cosmic island. Our solar system, consisting of the Sun, Earth, the other planets, and countless smaller bodies, is just one tiny, tiny speck within one of these islands. Let's start with a scale we can almost grasp. Our solar system. The Earth orbits the Sun at an average distance of about 50 million kilometers, which we call one astronomical unit, or AU. Light, travelling at its incredible speed of 299,922 kilometers per second, takes about 8 minutes to cover that distance. Now, consider the outermost planet, Neptune, which is about 30 AU from the Sun. Light takes roughly 4 hours to reach Neptune, but our solar system extends much further. The Oort cloud, a vast spherical shell of icy objects, is thought to stretch out to about 100,000 AU from the Sun. At that distance, light takes almost 2 years to travel from the Sun to the edge of its gravitational influence. So even our immediate cosmic neighbourhood is already mind-bogglingly immense. To put that into a more relatable scale, if the Sun were a grapefruit in New York City, the Earth would be a grain of sand orbiting it from a distance of 10 meters, and the Oort cloud would stretch halfway to California. This immense emptiness, even in our own solar system, is a recurring theme in the cosmos. Now, imagine billions of these grapefruit-sized solar systems, each with their own planets and Oort clouds, all clustered together in a colossal structure. That's essentially what a galaxy is. Our Sun is just one of these stars, located in one of the spiral arms of the Milky Way. We are not at the centre. We are about 2/3 of the way out from the galactic core, nestled in what's called the Orion Arm. This position gives us a unique perspective, allowing us to look both inwards towards the bright, dense galactic centre and outwards towards the sparser edges. This internal vantage point is both a challenge and a source of wonder, as we piece together our cosmic address from within. The Milky Way is classified as a barred spiral galaxy. This means it has a central bar-shaped structure composed of stars, from which spiral arms extend outwards. Imagine a colossal flattened disk, slowly rotating in space. This disk is where most of the stars, gas and dust are concentrated. Our galaxy's disk is enormous. From one edge to the other it spans approximately 100,000 to 20,000 light-years. To put that in perspective, 1 light-year is the distance light travels in 1 Earth year, roughly 9.46 trillion kilometers. So the Milky Way is about 946,000 kilometers across. Writing out that number doesn't even begin to convey the scale. If you could travel at the speed of light, it would take you 100,000 years to cross our galaxy from one side to the other. And remember, nothing with mass can even reach the speed of light. Even a photon travelling at the ultimate cosmic speed limit would spend an entire human lifetime just traversing our galactic home. The disk isn't perfectly flat, it has a thickness, much like a pancake. In its densest regions, the disk is about 1,000 light-years thick, so it's a vast, thin cosmic plate. Within this disk, the spiral arms are regions of higher density, where star formation is more active. Our Sun, as mentioned, resides in the Orion Arm, which is a relatively minor arm or perhaps a spur extending from a larger arm. The entire disk rotates, but not as a solid body. Stars closer to the centre complete an orbit faster than those further out, a phenomenon known as differential rotation. Our Sun, for instance, takes about 230 million years to complete one full revolution around the galactic centre. The last time the Sun was in its current position, dinosaurs were just beginning to roam the Earth, and the supercontinent Pangaea was still largely intact. At the very heart of this galactic disk lies the central bulge, a much thicker, roughly spherical region packed with older, reddish stars. This bulge is about 10,000 light-years across and 7 light-years thick. At its very centre, we find a supermassive black hole known as Sagittarius A, pronounced Sagittarius A star. This behemoth has a mass equivalent to about 4 million suns, and its gravitational pull is what orchestrates the frantic dense motions of stars in the galactic cores. We know it's there not because we can see the black hole itself, by definition light cannot escape it, but because we observe stars orbiting an invisible point at incredible speeds, their trajectories definitively pointing to a massive compact object that fits all the criteria for a supermassive black hole. The precision with which we can track these stellar orbits, even through thick interstellar dust, is a triumph of modern astronomy. Surrounding the entire disk and bulge is a vast, roughly spherical region called the galactic halo. This halo is much more diffuse, containing very old stars, hundreds of globular clusters, dense spherical collections of hundreds of thousands of stars like ancient cosmic beehives, and, most significantly, the vast majority of the Milky Way's dark matter. The dark matter halo is thought to extend far beyond the visible disk, perhaps out to 300,000 light-years or even more. We can't see dark matter. It doesn't interact with light or other electromagnetic radiation, but its gravitational influence is undeniable. Without it, the outer stars of our galaxy would fly off into intergalactic space because the visible matter alone doesn't provide enough gravitational pull to hold the galaxy together. This gravitational discrepancy observed in the rotational speeds of stars far from the galactic center was one of the earliest pieces of compelling evidence for dark matter, a concept we'll delve into much deeper in a later chapter. The Milky Way, therefore, is not just a collection of stars. It's a complex, dynamic system dominated by an invisible, gravitationally powerful force. How do we know all this when we're trapped inside? It's a testament to human ingenuity. Astronomers use various methods, mapping the distribution of different types of stars. Some are young and bright, tracing spiral arms. Others are old and found in the bulge or halo, observing the Doppler shift of radio waves emitted by hydrogen gas clouds to determine their motion and distance, much like how a police radar gun works, and using infrared telescopes that can penetrate the thick dust clouds that obscure our view of the galactic center. Each piece of information, like a single puzzle piece, slowly builds up the complete picture. The precise rotation curves of stars and gas, for instance, tell us about the distribution of mass, including the unseen dark matter throughout the galaxy. The sheer scale of the Milky Way is almost impossible to internalize. When we look up at the night sky and see that faint, shimmering band of light, often called the Milky Way band, we are seeing the combined glow of billions of stars. Many of these stars are so far away that their light has travelled for thousands of years to reach our eyes. That faint glow is the collective light from a cosmic city, a city so vast that if you were to travel from our Sun to its nearest stellar neighbour, Proxima Centauri, it would take you over 4 years, even at the speed of light. The distances between stars are not mere miles or kilometres, they are light years, representing voids of truly astronomical proportions. The emptiness is perhaps the most striking implication of this vastness. Even within the densest parts of the spiral arms, space is overwhelmingly empty. If our Sun were a grain of sand, the nearest star, Proxima Centauri, another grain of sand, would be over 100 kilometres away. The chance of 2 stars colliding, even in the bustling galactic core, is vanishingly small, more likely to happen over billions of years than in a human lifetime. Galaxies are mostly empty space, and the solidity we perceive is an illusion of immense scales and powerful electromagnetic forces. When you touch a wall, you're not actually making physical contact with its atoms. You're feeling the repulsion of electron clouds, a force that feels incredibly solid to us, but on a cosmic scale, it's just a subtle nudge. And yet, within this vast emptiness, there is incredible beauty and intricate order. Stars are born in nebulae, live out their lives and eventually die, sometimes in spectacular supernovae, enriching the galaxy with heavier elements, the very elements that make up our planet and our bodies. Our Sun is a third-generation star, meaning it formed from the remnants of previous stars that had already lived and died, scattering their processed material into space. Every atom of carbon in your body, every atom of oxygen you breathe, was forged in the heart of a star that lived and died billions of years ago, before our Sun was even born. We are, quite literally, stardust, part of the continuous cosmic cycle within this immense galactic home. It's a humbling and awe-inspiring thought that our very existence is tied to the grand, majestic processes unfolding across these incomprehensible distances. So we've established that our Milky Way is a truly immense structure, a sprawling island of hundreds of billions of stars, gas, and mysterious dark matter, spanning over 100,000 light-years across. It's a vast cosmic city, and our solar system is just one minuscule address within it. But as we hinted earlier, the Milky Way is not alone in the universe. It is just one galaxy among trillions. The question naturally arises, what is beyond our galactic city limits? What other islands of stars are nearby, and how do they relate to us? In our next chapter, we will venture just a little further out, beyond the halo of the Milky Way, to meet our closest galactic neighbours and begin to grasp the concept of our local group of galaxies. We'll see how galaxies interact and what their proximity tells us about the universe's dynamic nature, setting the stage for even grander scales. We've journeyed deep into the heart of our own colossal island of stars, the Milky Way, and then spiralled out to its farthest unseen edges, where the dark matter halo silently reigns. We've grasped its immense scale, 100,000 light-years across a flattened disk of hundreds of billions of stars, gas, and dust. But what happens when we finally break free from its gravitational embrace, when we leave the comfort of our galactic home? What do we see, and what new scales of incomprehension await us? Imagine for a moment that we possess the ultimate spaceship capable of instantaneously leaping across unimaginable distances. We push a button, and in a blink we're no longer within the Milky Way, we're outside it. Looking back at that majestic luminous spiral, a cosmic pinwheel slowly turning in the void, it's a breathtaking sight, a vision no human eye has ever beheld firsthand. From this vantage point, our galaxy would appear as a vast, shimmering disk, its spiral arms unfurling like celestial ribbons, its central bulge glowing with the collective light of billions of suns. But as we admire our home galaxy, our eyes begin to adjust to the deeper cosmic tapestry. We notice that the surrounding space isn't entirely empty. Far from it, scattered across the darkness like distant diamonds on black velvet, are other galaxies. Some are small, faint smudges of light, barely discernible. Others are grand, swirling behemoths, rivaling our own Milky Way in their splendour. These are our neighbours, our cosmic companions in the vast silent expanse. We are not alone in the universe, and our galaxy is not an isolated outpost. It is part of a much larger, gravitationally bound family of galaxies, a sprawling cosmic neighbourhood known as the local group. Think of it as a small exclusive club of galaxies, all dancing to the tune of mutual gravity. And among these neighbours, one stands out dominating the view, the magnificent Andromeda Galaxy, also known as Messier 31 or M31. If you have ever looked up at a truly dark night sky, far from city lights, you might have caught a glimpse of it yourself, a faint fuzzy patch of light, like a tiny cloud in the constellation Andromeda. That faint smudge is the light from 1 trillion stars, an entire galaxy, visible to the unaided eye even though it's 2.5 million light-years away. Let that sink in for a moment. The light you see from Andromeda began its journey 2.5 million years ago, long before humans walked the Earth. It's a journey through time as much as through space. Andromeda is a grander spiral galaxy than our own, a true cosmic monarch. It's estimated to contain roughly twice as many stars as the Milky Way, perhaps 1 trillion compared to our galaxy's 200 to 400 billion. Its disk stretches across an astounding 20,000 light-years, significantly wider than our Milky Way. Just like our galaxy, it has a central bulge, a halo, and its own supermassive black hole at its core, a gravitational behemoth even larger than Sagittarius A. But here's the most astonishing fact about Andromeda, the one that truly expands the mind. It's hurtling towards us. Yes, you read that correctly. Our two colossal galaxies, the Milky Way and Andromeda, are on a collision course. They are rushing towards each other at an incredible speed of approximately 110 kilometers per second, or about 250,000 miles per hour. This isn't just a casual drift, it's a gravitational embrace that will culminate in a spectacular cosmic ballet. Don't worry though, you won't need to duck for cover. This cosmic encounter is still a long way off, roughly 4.5 billion years in the future. By then, our sun will be nearing the end of its life, swelling into a red giant. When the collision does occur, it won't be a catastrophic smash-up in the way we usually imagine. Galaxies are mostly empty space, vast expanses between stars. It's like two clouds passing through each other, or two swarms of bees flying into one another. Individual stars are incredibly unlikely to collide. Instead, the gravitational forces will warp and stretch both galaxies, triggering bursts of star formation as gas and dust clouds are compressed. Eventually, over billions of years, our two magnificent spirals will merge, coalescing into a single, larger, elliptical galaxy that astronomers have playfully dubbed Milkomeda, or Milkdromeda. It's an awe-inspiring thought, a testament to the dynamic, ever-changing nature of the universe. As we continue our journey through the local group, we encounter another significant player, the Triangulum Galaxy, or M33. Located about 1.3 million light-years from us, it's the third largest member of our cosmic neighbourhood. Triangulum is a beautiful face-on-spiral galaxy, smaller than both the Milky Way and Andromeda, containing an estimated sub-40 billion stars. It's thought to be gravitationally bound to Andromeda, perhaps even orbiting it, making it a satellite in its own right within the larger local group framework. But the local group isn't just made up of these three giants, far from it. While Andromeda, the Milky Way and Triangulum dominate in terms of size and stellar population, they are surrounded by a retinue of smaller, less glamorous companions, the dwarf galaxies. These are humble collections of stars, often irregular in shape, containing anywhere from a few million to a few billion stars. They are the most numerous type of galaxy in the universe, and they are abundant in our local group. Our own Milky Way has several dwarf companions, the most famous of which are the Schedule Large Magellanic Cloud, LMC, and the Pole Small Magellanic Cloud, SMC. These irregular dwarf galaxies are visible to the naked eye from the southern hemisphere, appearing like detached pieces of the Milky Way, shimmering in the night sky. They are orbiting our galaxy, gradually being pulled in by its immense gravity, and will eventually be absorbed into our galactic disk. Similarly, Andromeda has its own family of satellite dwarf galaxies, like M32 and M110, which are currently being tidally stripped and consumed by their larger host. In total, the local group contains over 80 known galaxies, most of them dwarfs. This entire cosmic collective, this gravitationally bound ensemble, spans an impressive diameter of approximately 10 million light-years. Within this vast sphere, our three major spirals, Milky Way, Andromeda, and Triangulum, are locked in a slow, majestic dance, orchestrated by the invisible hand of gravity and the pervasive influence of dark matter. It's crucial to remember, however, that even within the local group, space remains overwhelmingly empty. While 110 million light-years sounds like a lot for a neighbourhood, the galaxies themselves are still separated by millions of light-years of near vacuum. If we were to shrink the Milky Way down to the size of a dinner plate, Andromeda would be another dinner plate about, 25 feet away. and the other 80 plus dwarf galaxies would be like scattered peas and grains of rice in a vast empty stadium. The emptiness is truly profound, making galactic collisions rare, slow-motion events. So we've expanded our understanding from our solitary star to our vast galaxy, and now to our immediate galactic neighborhood, the local group. But our journey doesn't end here. The universe, in its grand design, operates on ever larger scales, building structures upon structures, like an unimaginably intricate cosmic fractal. The local group itself is not an isolated island in the cosmic ocean. It is merely a small outpost on the fringes of a much grander structure, the Virgo supercluster. Imagine the local group as a tiny village. The Virgo supercluster would be the sprawling metropolitan area that village belongs to. What exactly is a supercluster? If a galaxy group like ours is a collection of dozens of galaxies, a galaxy cluster is a much larger aggregation, containing hundreds or even thousands of galaxies, often bound together by even stronger gravitational forces and vast amounts of hot, X-ray emitting gas. The Virgo cluster, for instance, is a massive cluster of galaxies, roughly 54 million light-years away from us, containing over 300 galaxies, possibly up to 2,000. It's the dominant gravitational center in our immediate cosmic vicinity. A supercluster, then, is an even larger structure, a colossal collection of multiple galaxy groups and galaxy clusters, all loosely bound by gravity. The Virgo supercluster, to which our local group belongs, stretches for an astounding 110 million light-years to cross. It contains over 100 galaxy groups and clusters, encompassing an estimated 1 million trillion suns. Our local group is just one tiny, relatively insignificant speck on its outer edge. But wait, there's more. Even the Virgo supercluster is not the ultimate structure. Recent discoveries have revealed that our entire Virgo supercluster is just a minor component of an even vaster, more complex cosmic leviathan. Laniakea. Hawaiian for immeasurable heaven. Laniakea is an immense supercluster, estimated to be 80 million light-years in diameter, containing the mass of 100 million billion suns spread across 100,000 galaxies. It's a vast river of galaxies all flowing towards a common gravitational attractor known as the Great Attractor, a mysterious region of immense mass. This hierarchical structure, stars within galaxies, galaxies within groups, groups within clusters, clusters within superclusters, and superclusters forming part of an even grander cosmic web, reveals the universe's intricate architecture. It's a universe that builds upon itself, from the minuscule to the incomprehensibly vast. You see, the question, how big is the universe, isn't just about a single number. It's about a progressive journey through scales that defy our intuition. We started with our humble Earth, then expanded to our solar system, then to our majestic Milky Way, a true island universe. Now, we've placed our galaxy within its immediate family, the local group, and then zoomed out further to the Virgo supercluster, and finally to the truly colossal Laniakea supercluster. Every step of this journey is a lesson in humility and wonder. You, reading these words, are a collection of atoms formed in the heart of stars, residing on a small planet, orbiting an average star, nestled in one of the spiral arms of a barred spiral galaxy, which itself is one of over 80 members of the local group, a tiny component of the Virgo supercluster, which in turn is a mere tendril within the vast expanse of Laniakea. The universe whispers its grand designs to us through these escalating scales. It challenges us to shed our anthropocentric perspectives and embrace a cosmic view. We are small, yes, infinitesimally so, but our minds, our curiosity, and our capacity for understanding are boundless. As we continue to peel back the layers of cosmic scale, we will confront even more mind-bending concepts, pushing the very limits of our imagination. The journey has only just begun. The universe is waiting to unfold its next breathtaking secret. We just left off marvelling at the colossal Laniakea supercluster, a truly immense structure spanning 520 million light-years, where our own Milky Way is merely a tiny speck, flowing along with hundreds of thousands of other galaxies towards the mysterious Great Attractor. But even Laniakea, as mind-bogglingly vast as it is not an isolated island in the cosmic ocean. No, it's merely a node, a dense knot in an even grander, more intricate architecture that weaves throughout the entire observable universe, the cosmic web. Imagine, if you will, the universe not as a uniform, evenly distributed soup of galaxies, but as a colossal three-dimensional spiderweb, or perhaps a vast, intricate neural network pulsing with unseen energy. This is the cosmic web, the largest known structure in the universe, an awe-inspiring framework of matter that stretches for billions of light-years, defining the very fabric of reality on the grandest scales. What does this cosmic tapestry look like? It's composed of three primary elements, all interconnected. First, there are the filaments. These are gargantuan, elongated strands of galaxies, gas and dark matter, stretching for hundreds of millions of light years. Think of them as the long, luminous threads of the spiderweb, along which galaxies are strung like pearls on a necklace. Our own local group, and indeed the entire Laniakea supercluster, resides within one such filament. We are not alone floating in random space. We are part of a cosmic river, flowing along one of these immense invisible currents. Where these filaments intersect, where several of these cosmic rivers converge, we find the second component, galaxy clusters. These are the densest knots in the web, veritable cosmic beehives containing thousands of galaxies bound together by immense gravitational forces. They are the most massive known structures in the universe, each weighing quadrillions of times the mass of our Sun. Within these clusters, galaxies often collide, merge, and interact in spectacular, violent ballets of gravitational force, stripping away gas and igniting new bursts of star formation. The Virgo cluster, a member of our Laniakea supercluster, is a smaller example of such a knot, though many clusters are far grander, home to true galactic metropolises. And then, between these luminous filaments and dense clusters, lie the third and perhaps most enigmatic elements, the cosmic voids. These are truly vast, almost empty regions of space, colossal bubbles that can span hundreds of millions of light-years across. If the filaments are the luminous threads of the web, the voids are the gaping holes within it. These are not entirely empty, mind you. They contain some galaxies, but they're incredibly clear, like isolated dust motes in a colossal dark chamber. They are the quiet, dark expanses where the universe truly shows its emptiness, challenging our imagination to grasp such profound nothingness on such a grand scale. It's an incredible mental leap, isn't it? From the familiar comfort of our home planet, to our Sun, to our galaxy, and now to the vast interconnected network that defines the universe. We are looking at a structure that is so immense, ancient, that it challenges our very understanding of scale. And just like with galaxies and superclusters, the architect behind this grand design, the invisible hand shaping these cosmic structures, is once again dark matter. Remember how we discussed dark matter in Chapter 1, this mysterious, undetectable substance that makes up about 127% of the universe's mass? Its gravitational influence is absolutely crucial for holding galaxies together and for shaping the large-scale structure of the cosmos. Without dark matter, the ordinary matter we can see, stars, planets, gas, dust, simply wouldn't have had enough gravitational pull to clump together into the galaxies, clusters, and filaments we observe today. The universe would be a much more uniform, less structured, and frankly far less interesting place. Think of it this way. The dark matter forms an invisible scaffolding, an underlying gravitational skeleton that permeates space. Ordinary matter, the stuff we are made of, then falls into this scaffolding, congregating along the densest regions of the dark matter web. It's like pouring water onto a crumpled cloth. The water will flow into the folds and creases, outlining the underlying structure. In the same way, galaxies and clusters trace out the contours of the invisible dark matter web. The filaments we see are essentially the densest concentrations of dark matter, attracting and holding together the luminous galaxies that we can observe. So how did this incredible cosmic web come to be? We need to rewind the cosmic clock all the way back to the very first moments after the Big Bang, nearly 13.8 billion years ago. In the incredibly hot, dense and uniform early universe, there were tiny, minuscule fluctuations in density, ripples in the fabric of space-time born from quantum process. These were the initial seeds, the almost imperceptible variations that gravity would then begin to amplify over billions of years. As the universe expanded and cooled, these tiny density enhancements, regions where there was ever so slightly more matter, especially dark matter, began to exert a stronger gravitational pull. Over eons, these regions attracted more and more matter, growing larger and larger. The slightly denser areas grew into the filaments and clusters, while the slightly less dense areas were stretched out into the vast empty voids by the universe's relentless expansion. It was a slow, majestic dance of gravity and expansion, sculpting the universe into the grand structure we observe today. We even have a baby picture of the universe that reveals these initial seeds, the Cosmic Microwave Background, CMB. This faint, uniform glow of microwave radiation, detected coming from every direction in space, is the afterglow of the Big Bang. It's light that was emitted when the universe was only about 380,000 years old. A mere infant compared to its current age. When we look at the CMB, we see tiny temperature fluctuations. Some regions are ever so slightly warmer, others ever so slightly cooler. These subtle variations correspond precisely to those initial density fluctuations that would eventually grow into the galaxies, clusters, filaments, and voids of the cosmic web. It's a direct observational link between the very early universe and the immense structure we see around us today. Our own local group, our home galaxy, and the entire Laniakea supercluster are all embedded within this immense cosmic web. We are not just floating in empty space, we are part of a vast interconnected system, a single thread in a cosmic tapestry woven from dark matter and ordinary matter, stretched across billions of light years. It's a humbling thought, isn't it? You, me, our planet, our solar system, our galaxy, all are integral parts of this incomprehensibly vast, dynamic structure. The sheer scale of the cosmic web, with its filaments stretching for hundreds of millions of light years, and its voids encompassing even larger regions, forces us to confront the true meaning of big. Our galaxy, the Milky Way, is a mere speck within one of these luminous threads. Even superclusters, those collections of hundreds of thousands of galaxies, are just the knots, the intersections in this grand design. As we journey further out into the cosmos, another profound realization dawns upon us. The universe is not static. It's not a fixed canvas upon which galaxies are painted. No, the universe itself is expanding, and it has been doing so ever since the Big Bang. This isn't just galaxies moving through space. it's space itself, expanding, carrying the galaxies along with it, like raisins in a rising loaf of bread. This expansion means that the farther away a galaxy is from us, the faster it appears to be receding. This phenomenon, first observed and theorized by astronomers like Edwin Hubble, is known as Hubble's law. We see the light from distant galaxies redshifted, meaning their light waves are stretched to longer, redder wavelengths as the space between us and them expands. It's like the Doppler effect for sound, but for light in an expanding universe. The more redshifted a galaxy's light is, the faster it's moving away from us, and thus the farther away it is. This cosmic expansion has profound implications for what we can actually observe. Because light travels at a finite speed, and because the universe has a finite age, 13.8 billion years, there's a limit to how far back in time, and thus how far in space we can see. We are constantly receiving light that has been travelling for billions of years, showing us galaxies as they were billions of years ago. The most distant light we can detect is the CMB, which shows us the universe as it was nearly 13.8 billion years ago. This creates our observable universe, a spherical region of space centered on us, from which light has had time to reach us since the Big Bang. Beyond this horizon, there are galaxies whose light simply hasn't had enough time to reach us, or whose distance has expanded so rapidly that their light will never reach us. The universe in its entirety is likely far, far larger than what we can observe. But that, my friend, is a story for the next chapter. For now, let's allow the sheer scale of the cosmic web to truly expand our minds. We are part of a structure so vast, so ancient, so intricately woven by the forces of gravity and dark matter that it humbles us to our core. Our scientific instruments, our telescopes, our minds, they reach out across these immense distances, piecing together this incredible cosmic puzzle, revealing the fundamental architecture of everything that exists. It's a testament to human curiosity, to our insatiable desire to understand our place in this magnificent, ever-expanding cosmos. And every piece of this puzzle, from the tiniest atom to the most colossal supercluster, whispers tales of creation, evolution, and the enduring mysteries that still await our discovery. We've peered into the vastness of the cosmic web, seen the universe's baby picture in the cosmic microwave background, and acknowledged the boundary of our observable universe. This observable sphere, centered on us, is the limit of what light has had time to reach us from since the Big Bang. But here's where the numbers truly begin to expand beyond easy comprehension, where the concept of size becomes a philosophical journey. You see, when we talk about the observable universe, we're not talking about a static, unchanging arena. Oh no, we are talking about a dynamic, ever-stretching cosmic canvas. If we were to calculate the distance light that could have travelled in the age of the universe, you might think it's simply the 13.8 billion light years in every direction, making our observable universe 27.6 billion light years across. A simple calculation, right? But the universe, my friend, is never simple. It's far more fascinating than that. That all 13.8 billion years is indeed the age of our universe, the time since the Big Bang. This figure, derived from meticulous observations of the cosmic microwave background and the expansion rate, represents the cosmic clock ticking away since everything began. It's the maximum age of any light we can possibly detect. But here's the kicker. The universe has been expanding during those 13.8 billion years. Imagine an ant crawling on the surface of a balloon. As the ant walks, the balloon is slowly inflating. The distance the ant travelled is one thing, but the distance between its starting point and its current location, as measured across the surface of the balloon, is constantly increasing due to the inflation. The light from the most distant galaxies we detect has been travelling for past the 13.8 billion years. But during that journey, the space itself between us and those galaxies has stretched immensely. It's like a cosmic treadmill where the finish line keeps moving further away even as you run towards it. So that while the light we see left those distant galaxies 13.8 billion years ago, those galaxies are now much further away. How much further? Hold on to your cosmic hats, because this is where the numbers truly take flight. Due to this relentless expansion, the edge of our yet observable universe is not 13.8 billion light years away, but a staggering 5 billion light years in every direction. That means our here observable universe is approximately some 93 billion light years in diameter. Take a moment, truly ponder that. 93 billion light years. That's almost 7 times. The distance light could have travelled in a static universe. It's a sphere so vast, so incomprehensibly immense, that it contains an estimated 2 trillion galaxies, each with hundreds of billions to trillions of stars. We're talking about 2,000 galaxies within our observable reach, and every single one of them is a colossal island of stars, gas, dust, and dark matter, just like our own Milky Way. This observable universe is our cosmic horizon, the limit of our sensory perception of the cosmos. It's the boundary beyond which the light simply hasn't had enough time to reach us. It's not a physical wall or an actual edge to the universe itself, but rather a temporal boundary, a window into the past. The cosmic microwave background, that baby picture of the universe, represents the very edge of this horizon, the oldest light we can possibly see, dating back to just 380,000 years. After the Big Bang, when the universe cooled enough for light to travel freely. But if this is just the observable universe, what about the entire universe? Is it finite like a giant cosmic bubble, or is it truly infinite, stretching on forever in every direction? This, my friend, is one of the grandest, most profound questions humanity has ever grappled with. And the answer, while not definitive, leans towards a scale that dwarfs even our 93 billion light-year observable sphere. The shape of the universe, its geometry, holds the key. Cosmologists describe the universe's overall shape using 3 possibilities. 1. Closed. Like the surface of a sphere, it curves in on itself. If you travelled in a straight line, you would eventually return to your starting point. This would imply a finite universe. 2. Open. Like the surface of a saddle, it curves outwards infinitely. This would imply an infinite universe. 3. Flat. Like a sheet of paper, it extends infinitely in all directions. This too would imply an infinite universe. Which one is it? We can determine the universe's geometry by measuring its overall density, the amount of matter and energy packed into it. If the density is above a critical value, the universe is closed. If it's below, it's open. If it's exactly at the critical value, it's flat. And what do our most precise measurements, particularly from the cosmic microwave background, tell us? They tell us that our universe is remarkably, almost perfectly flat, or if it's truly flat, then it must be infinite. Think about that for a moment. An infinite universe. A universe that, no matter how far you travel, no matter how many trillions of galaxies you pass, never, ever ends. If the universe is indeed infinite, then the question, how big is the universe, becomes almost nonsensical. It's not a size, it's all sizes. It's an endless repetition of cosmic structures, an infinite expanse of space, time, matter, and energy. Every possible configuration of matter, every possible event, would not just happen, but would happen infinitely many times, across the abundant expanse. You, reading these words, would exist an infinite number of times in infinite identical copies of the Milky Way, within an infinite number of identical local groups, within an infinite number of identical cosmic webs. Even if the universe isn't strictly infinite, but merely flat enough that its curvature is beyond our ability to detect, it would still have to be mind-bogglingly enormous. Calculations suggest that if the universe is finite but flat, its true size would be at least 250 times larger than our observable universe. So multiply that to 93 billion light years by 150. That gives us a diameter of approximately 3.25 trillion light years. Trillion light years. We're no longer talking about numbers that fit neatly into our heads. We are talking about numbers that stretch the very fabric of our imagination to its breaking point. This is the scale of the universe that lies beyond our cosmic horizon, beyond the reach of our telescopes, beyond the light that has had time to travel to us. It's more galaxies, more clusters, more voids, more dark matter, more dark energy, all stretching out into the unseen. What lies beyond our observable horizon isn't fundamentally different from what we see within it. It's simply more of the same cosmic tapestry, but its light hasn't reached us yet. Imagine standing in the middle of a vast, foggy plain. You can only see a certain distance, but you know the plain continues on beyond the fog. The fog is the 13.8 billion years of cosmic time, and beyond it the plain stretches. So to answer the question, how big is the universe compared to our galaxy? The answer is impossibly, unimaginably, perhaps infinitely larger. Our magnificent Milky Way, a colossal island of hundreds of billions of stars, is but a single speck within the 2 trillion galaxies of our observable universe. And that observable universe is, in turn, a tiny fleeting bubble within a cosmos that might stretch into true infinity, or at the very least, into a realm so vast the number 0.25 trillion light years sounds like a whisper in the wind. This journey through the scales of the cosmos, from our solar system to the potentially infinite universe, is not just an exercise in numbers. It's an invitation to humility, a call to wonder, and a profound reminder of our place. We are tiny, yes, but we are also the universe's way of understanding itself. We are the consciousness that can look out at 3 billion light years of observable space, contemplate the 2 trillion galaxies within it, and then dare to ask, what lies beyond? The universe, in its boundless majesty, continues to whisper its secrets to us, inviting us to explore, to question, and to marvel. And with every new discovery, with every new layer of scale we uncover, our understanding of how big expands, pushing the boundaries of what we thought was possible, and reaffirming the extraordinary privilege of being here, now, to witness it all. We've journeyed far, haven't we? From the familiar comfort of our home planet, we've stretched our minds to encompass the vast, sprawling arms of the Milky Way, then sailed through the local group, navigated the tendrils of the cosmic web, and finally stood at the precipice of the observable universe, a staggering sphere, 93 billion light years in diameter, teeming with an estimated 2 trillion galaxies. Each one, an island unto itself, a cosmic city of stars, gas and dust, echoing the grandeur of our own galactic home. You might think, surely this is it. This is the ultimate limit, the grandest scale our minds can possibly grasp. But what if this colossal expanse, this seemingly infinite tapestry of stars and galaxies, is just one thread in an even larger, more intricate design? What if our universe isn't the only universe? This is where science truly begins to mingle with philosophy, where the known gives way to the tantalizingly possible, and where our understanding of everything expands beyond the wildest imaginings. We're talking about the multiverse, a concept that posits the existence of multiple universes, perhaps infinite in number, each with its own unique properties, dimensions, and even laws of physics. It's a truly mind-bending idea, one that shifts our perspective from being inhabitants of a single, immense cosmos to potentially being residents of a tiny speck within an unimaginably larger cosmic foam. To truly ponder the multiverse, we must first acknowledge its speculative nature. Unlike the cosmic microwave background, or the whole redshift of distant galaxies, we have no direct observational evidence of other universes. Yet several compelling theoretical frameworks rooted in our current understanding of physics suggest that the multiverse isn't just a flight of fancy, but a logical, perhaps even inevitable consequence of how our own universe operates. Consider, for instance, the theory of one with cosmic inflation. We touched upon the Big Bang, the cataclysmic event that birthed our universe 13.8 billion years ago. Inflation is a proposed period of extremely rapid exponential expansion that occurred in the first fleeting moments after the Big Bang, smoothing out the universe and sowing the seeds for the large-scale structures we observe today. But what if this inflationary process isn't a one-time event? What if it's an eternal process, continuously churning out new bubble universes as it expands? Imagine a vast, ever-inflating ocean where our universe is just one of countless bubbles forming, detaching, and growing within it. Each bubble could then evolve independently, perhaps with different fundamental constants, or even a different number of spatial dimensions. This is the eternal inflation multiverse, an awe-inspiring vision where new universes are constantly being born, a cosmic nursery on an unimaginable scale. Then there's the concept of parallel universes arising from quantum mechanics. You're familiar with the bizarre nature of the quantum realm, where particles can exist in multiple states simultaneously until observed. This is often described by the many worlds interpretation, which suggests that every time a quantum measurement is made, every possible outcome actually occurs, each branching off into its own separate non-interacting universe. In this view, every decision you've ever made, every path not taken, exists in a parallel reality. While this particular interpretation is highly debated, it offers a fascinating glimpse into how different versions of reality might coexist, hidden from our direct perception. It's like watching a movie where every possible plot twist, every alternate ending plays out in its own separate screening room simultaneously. And what about what brain worlds? This theory, often associated with string theory, proposes that our entire universe, with its 3 spatial dimensions and 1 time dimension, is but a brain, a higher dimensional membrane, floating within a larger, higher dimensional space, sometimes called the bulk. Imagine our universe as a sheet of paper, and other universes as other sheets of paper, all stacked together in a cosmic ream. These brains could be incredibly close to each other, yet separated by an extra dimension, preventing direct interaction. Collisions between these brains, some theories suggest, could even be the origin of new Big Bangs. It's a truly wild thought that the very fabric of our reality might be just a thin skin on a much grander, more complex cosmic entity. The implications of a multiverse are profound, shaking the very foundations of our understanding. If there are infinite universes, then it's statistically probable that every conceivable possibility exists somewhere. Universes identical to ours where you made a different breakfast choice this morning. Universes where the laws of physics are slightly off, preventing stars from forming or life from emerging. Universes where gravity repels instead of attracts. The sheer scope of this idea is almost too much for the human mind to bear. It pushes against the very limits of our comprehension, forcing us to redefine what big truly means. You see, our journey has been one of constant re-evaluation, hasn't it? We started with the familiar, then expanded to the colossal, and now we're wrestling with the concept of the infinitely many colossal. This highlights a fundamental aspect of human existence, our limited perception. We are creatures of three spatial dimensions bound by the speed of light and confined to a relatively tiny corner of space and time. Our senses evolved to help us navigate a terrestrial environment, not to perceive the curvature of space-time or the subtle dance of quantum particles, let alone the existence of other universes. Yet despite these limitations, our minds, armed with the tools of science and mathematics, have managed to construct models and theories that push beyond the immediate and the observable. It's a testament to our insatiable curiosity, our drive to understand the fundamental nature of reality. Every new telescope, every particle accelerator, every theoretical breakthrough is another step towards unraveling the universe's grand designs, or perhaps the grand designs of the multiverse. Think about the sheer improbability of life, of us existing in our universe. The fundamental constant, the strength of gravity, the electromagnetic force, the masses of elementary particles, seem finely tuned for stars to form, for complex chemistry to emerge, for life as we know it to exist. If any of these values were even slightly different, our universe might be a barren, lifeless void. This fine-tuning problem is often cited as a puzzle, but in a multiverse scenario, it might not be a problem at all. If there are countless universes with varying physical laws, then it's simply a matter of statistical probability that some of them would have the right conditions for life. We just happen to inhabit one of those fortunate universes precisely because we can exist here. This perspective doesn't diminish the wonder of our existence. If anything, it amplifies it. To be a conscious being in this universe, capable of contemplating the possibility of other universes, is an almost impossibly rare and beautiful thing. It underscores the preciousness of our own cosmic home and the unique conditions that allowed us to emerge. So, if there are potentially infinite universes, does that mean there's an infinite number of Earths? An infinite number of you? In some multiverse models, particularly those based on the eternal inflation where initial conditions can vary, the answer could be a resounding yes. If the universe is truly infinite, or if the multiverse is infinite, then every possible arrangement of particles, every possible history, must eventually repeat itself. This means that at some unimaginable distance, there could be another Earth, another Milky Way, another you, reading these very words. It's an idea that is both exhilarating and terrifying, a profound challenger to our sense of individuality and uniqueness. But let's bring it back to what we know, to the observable universe and its 2 trillion galaxies. Even without venturing into the realm of the multiverse, the numbers alone suggest an almost certainty of life beyond Earth. With billions of stars in each galaxy, and potentially billions of planets orbiting those stars, the sheer combinatorial possibilities are staggering. The conditions for life might be rare, but with such an immense canvas, the probability of them occurring elsewhere becomes incredibly high. This is the essence of the Sumwalt-Drake equation, a probabilistic argument for estimating the number of active communicative extraterrestrial civilizations in the Milky Way galaxy. While it yields no definitive answer, it forces us to confront the vastness of the cosmic playground. Then comes the Fermi paradox. If alien civilizations are so probable, Where are they? Why haven't we detected any signs of intelligent life? Is it because interstellar travel is too difficult? Are civilizations inherently self-destructive? Are we simply looking in the wrong ways, or are we too primitive to recognize their signals? Or perhaps, is life truly rarer than we imagine, even in a universe of 2 trillion galaxies? The silence of the cosmos remains one of its most profound mysteries, a question that continues to drive our astronomical endeavours. Our journey through the cosmos has been one of constant expansion, both of scale and of understanding. We began with the familiar, stepped into the awe-inspiring, and now stand on the edge of the truly incomprehensible. From the 100,000 light-years of our Milky Way to the 93 billion light-years of the observable universe, and then to the theoretical possibility of a multiverse of infinite universes, our perspective has been stretched to its absolute limit. What does this mean for us? Tiny beings on a pale blue dot, orbiting an average star in an ordinary galaxy, within a potentially infinite cosmic tapestry. It means that the quest for knowledge is endless. Every answer uncovers a dozen new questions. Every horizon we reach reveals a new, more distant one. Our James Webb Space Telescope peers back in time, showing us the universe as it was just a few 100 million years after the Big Bang, revealing galaxies in their infancy. Future observatories, both on Earth and in space, will continue to push these boundaries, probing the earliest moments, mapping the distribution of dark matter with unprecedented precision, and perhaps one day even finding faint echoes of other universes. The universe, in all its majestic and mysterious glory, continues to whisper its secrets to those willing to listen, to those brave enough to ask the biggest questions. You, the reader, are a part of this grand cosmic narrative. Your capacity to comprehend these scales, to feel the awe and humility that comes with such knowledge, connects you to the greatest journey of discovery humanity has ever undertaken. We are small, yes, but our minds are vast, capable of encompassing galaxies, superclusters, and perhaps even the boundless expanse of the multiverse itself. The journey continues, and the universe, in all its infinite possibilities, awaits our further exploration. So, we've peered into the theoretical realms of the multiverse, where countless universes might bloom and fade, each potentially governed by its own unique set of physical laws. We've stretched our minds to the very edges of what science might one day confirm or perhaps forever leave to the realm of philosophical inquiry. But even within our universe, the one we know exists, the one we inhabit, there remain profound, mind-bending mysteries that continue to challenge our understanding and fuel our insatiable curiosity. These are the known unknowns, the vast cosmic puzzles that stand as testament to how much more there is to discover, even after our staggering journey from Earth to the cosmic web. Let's return to 2 of the most enigmatic components of our universe, the invisible architects and drivers of its grand design: dark matter and dark energy. Remember how we saw dark matter forming the invisible scaffolding for the cosmic web, gathering galaxies into clusters and superclusters? It's the gravitational glue that holds everything together, preventing galaxies from simply flying apart. We estimate it makes up about of the universe's total mass and energy. But what is it? We don't see it. It doesn't interact with light or other electromagnetic radiation, which is why it's dark. It doesn't absorb, reflect, or emit light. We only infer its existence through its gravitational effects on visible matter, the way galaxies spin faster than they should, the way light bends around massive galaxy clusters. Imagine a vast, invisible ocean in which all the luminous galaxies are mere boats, its currents dictating their every move. We are trying to map these currents without ever seeing the water itself. Scientists are on a relentless quest to identify dark matter. Is it made of exotic, undiscovered particles that only interact weakly with normal matter? Perhaps WIMPs, weakly interacting massive particles? Could it be primordial black holes formed in the early universe? Or something even stranger, a modification to our understanding of gravity itself? Experiments deep underground, shielded from cosmic rays, meticulously search for the faintest interaction of these elusive particles. Telescopes map the gravitational lensing effects across vast stretches of space, trying to trace the distribution of this invisible mass. It's like trying to understand an elephant by only observing the ripples it makes in a pond. The hunt for dark matter is one of the most exciting frontiers in physics, a cosmic detective story playing out on the grandest scale. And then there's dark energy, an even more perplexing enigma. If dark matter is the cosmic glue, dark energy is the cosmic accelerator. It's the mysterious force responsible for the accelerating expansion of the universe. When we first observed distant supernovae, we expected the universe's expansion to be slowing down due to the gravitational pull of all its matter. Instead, we discovered it was speeding up. This implies an unknown force, a repulsive pressure inherent to space itself, pushing everything apart. Dark energy is estimated to constitute a staggering concept of the universe's total mass energy content. Think about that. Almost 95% of our universe is made of stuff we can't see and don't understand. We, the visible matter, the stars, planets, and ourselves, are merely a tiny % of the cosmic pie. What is dark energy? Is it the energy of the vacuum itself, predicted by quantum mechanics but with a value far too small to explain the observed acceleration? Is it a new dynamic field, a quintessence that permeates space? Or does it point to a fundamental flaw in Einstein's theory of gravity on cosmic scales? The implications are profound. Dark energy will dictate the ultimate fate of our universe. Will it continue to accelerate until galaxies are flung so far apart that the night sky becomes an empty void, a big freeze or heat death? Or will it become so powerful that it tears apart galaxies, stars, planets, and even atoms in a big rip? We don't know. The universe is whispering its secrets, but we are still learning its language. Beyond these invisible forces, the question of the universe's true size and geometry remains tantalizingly open. We've journeyed to the edge of the observable universe, a sphere 93 billion light years in diameter, our cosmic horizon. But what lies beyond? Is the universe truly infinite? Our current observations, particularly of the cosmic microwave background, suggest a remarkably flat geometry. This flatness implies that the universe is either truly infinite, or at least so incredibly vast, perhaps 23.25 trillion light years, cross as we discussed, that it appears flat within our observable patch. Imagine you're standing on a vast, perfectly flat desert. You can see for miles, and it appears infinite. But if you were to travel far enough, you might eventually discover that the desert is actually part of a giant sphere, or a saddle shape, just so huge that its curvature is imperceptible from your vantage point. We are like ants on that desert trying to determine the shape of the entire Earth. The sheer scale makes it almost impossible to comprehend. Is there an edge to reality? Does space simply continue forever, filled with an endless tapestry of galaxies, clusters, and voids, repeating patterns or forever evolving? Or does it curve back on itself like the surface of a sphere, so that if you travelled far enough in a straight line, you would eventually return to your starting point, albeit billions of years later? These are not mere philosophical musings, they are active areas of cosmological research, with implications for everything we understand about existence. And what of the multiverse? While still speculative, The various theories, eternal inflation, many worlds interpretation, brain worlds, offer a humbling perspective on our own cosmic island. If our universe is just one bubble in an infinite foam, one quantum outcome among countless others, or a membrane floating in a higher dimension, then our perception of the universe is merely a tiny fraction of a far grander reality. This idea profoundly shifts our understanding of probability. If there are infinite universes, then every possible outcome, no matter how improbable, must exist somewhere. This means there could be universes where the laws of physics are wildly different, where gravity is repulsive or where light travels at a snail's pace. It suggests a vastness that transcends even our most expansive cosmic journey, pushing the boundaries of what big truly means. Amidst all this grandeur, this unimaginable scale, this symphony of knowns and unknowns, there lies another profound mystery, the Fermi paradox. We've seen that our galaxy, the Milky Way, contains hundreds of billions of stars, and the observable universe contains 2 trillion galaxies, each potentially harboring billions of stars. Many of these stars are orbited by planets, and a significant fraction of those planets are likely to be in the habitable zone, the right distance from their star for liquid water to exist. Given the sheer numbers, the probability of life, and even intelligent life, arising elsewhere seems astronomically high. So where are they? Why do we not see any evidence of advanced extraterrestrial civilizations, no signals, no megastructures, no signs of cosmic engineering? Are we truly alone, or is there something about the journey from simple life to advanced civilization that creates a great filter, a barrier so difficult to overcome that it prevents most life from reaching a detectable stage? Perhaps the filter lies in our past, the origin of life, the jump from single-celled to multicellular organisms, the rise of intelligence. Or perhaps it lies in our future, self-destruction through technology, environmental collapse, or some cosmic catastrophe. The Fermi paradox forces us to confront our own existence, our own uniqueness, and the incredible improbability of our being here, conscious and capable of asking these questions on this pale blue dot. The quest for answers to these cosmic riddles defines humanity's scientific endeavour. We build ever more powerful telescopes like the James Webb Space Telescope, peering back in time to the universe's infancy, searching for the first stars and galaxies, and analysing the atmospheres of exoplanets for signs of life. We construct massive particle accelerators, like the Large Hadron Collider, to recreate the conditions of the early universe, hoping to glimpse the elusive particles of dark matter or understand the fundamental forces that govern everything. We develop sophisticated theoretical models, using mathematics as our language to describe realities we cannot directly observe. This journey, from the familiar comfort of our home planet to the mind-bending edges of the observable universe and the theoretical multiverse, is not just about numbers and distances, it's about perspective. It's about understanding our place, not at the centre of everything, but as a tiny, yet incredibly significant part of an unimaginably vast and complex whole. You are a collection of atoms forged in the heart of stars, part of the cosmic cycle that has been unfolding for 13.8 billion years. You are capable of contemplating scales and concepts that would make ancient philosophers weep with awe. So how big is the universe compared to our galaxy? We've seen that our galaxy, the Milky Way, a majestic spiral of 100,000 light years across, housing hundreds of billions of stars, is but a single island in a local group of a few dozen galaxies. That local group is a tiny speck in the Virgo supercluster, which is itself a mere tendril in the colossal Laniakea supercluster, all flowing towards the Great Attractor. These superclusters are just nodes in the vast filamentary cosmic web, a structure spanning billions of light years. and that entire observable universe, encompassing 2 trillion galaxies and stretching 93 billion light years across, is just the part we can see. Beyond our cosmic horizon, the universe could be truly infinite, or so vast that our observable patch is like a single atom in a planet-sized organism. And beyond that, there could be a multiverse of infinite universes, each with its own laws, its own cosmic story. Our galaxy is not merely small, it is an almost infinitesimally tiny, precious haven within a reality so immense that the word big loses all meaning. It is a single glowing ember in an endless cosmic fire. Yet it is within this tiny ember that consciousness has arisen, that we have developed the capacity to ask these questions, to map the stars, to ponder the existence of dark matter and dark energy, and to dream of multiverses. This journey through the cosmos is far from over. Each discovery opens up new questions, each answer reveals deeper mysteries. The universe continues to unfold, revealing its secrets gradually, patiently. And we, with our insatiable curiosity and our relentless pursuit of knowledge, are here to witness it, to study it, and to continue asking the most profound question of all. What else is out there? The universe, in its boundless majesty, continues to whisper, and we continue to listen, forever humbled, forever inspired, and forever seeking to understand the grand design of it all. We've journeyed together across the cosmos, from the familiar glow of our Milky Way to the colossal filaments of the cosmic web, pushing the boundaries of what we can see and comprehend. We've acknowledged the 2 trillion galaxies within our observable reach, a staggering number that already challenges the imagination. But as we stand at this precipice of understanding, staring out into the vast silent expanse, we must confront the most profound truth of all. The universe, in its grand design, holds more questions than answers. The true enormity isn't just in the numbers we've tallied, but in the unseen, the unknown, the unimagined, that lies beyond our current grasp. Think for a moment about those dominant forces we discussed: dark matter and dark energy. They are the silent architects, the invisible puppeteers pulling the strings of cosmic evolution. Dark matter, the gravitational glue holding galaxies and clusters together, makes up roughly 20% of the universe's mass energy content. Yet we cannot see it, we cannot touch it, we cannot directly detect it. Its presence is inferred only by its gravitational effects, like a phantom dancer whose steps we can trace by the movement of the stage, but whose form remains utterly elusive. What is it? Is it a new particle, an exotic form of matter, or a fundamental modification of gravity itself? The scientific community is a collective detective, setting traps, building sophisticated underground laboratories, and launching space telescopes, all in pursuit of this ghost in the machine. Imagine trying to understand a complex engine when 7% of its components are entirely invisible to you, yet crucial to its operation. That's our cosmic predicament. And then there's dark energy, the truly enigmatic force comprising a staggering 10% of the universe. This isn't just invisible, it's anti-gravitational. It's the engine accelerating the universe's expansion, pushing galaxies apart at ever-increasing speeds, shaping the ultimate fate of the cosmos. Without it, the universe might have collapsed back on itself. With it, we face a future where galaxies drift so far apart that the night sky might eventually become utterly dark, save for our own local group. We understand its effect, but its nature remains a profound mystery. Is it a property of space-time itself, as Einstein's cosmological constant suggested? Is it the manifestation of a dynamic field fluctuating through time? Or is it something even more exotic, something that challenges our most fundamental theories of physics? It's like watching a boat accelerate away from you, knowing something is propelling it, but having no idea what that something is. This isn't just a missing piece of the puzzle, it's the entire frame, the entire backdrop upon which the puzzle is laid. These two dark components are not mere footnotes in the cosmic story, they are the main characters, dictating the universe's structure and destiny, and yet they exist beyond our direct perception, forcing us to admit the profound limits of what we can currently know. Our understanding of the universe, for all its advances, is still built upon a foundation where % of the building blocks remain utterly unknown. You might feel a pang of frustration, a sense of incompleteness, and you'd be right. But I'm always curious, isn't there also an exhilarating thrill in knowing that such grand mysteries still await our discovery? The universe isn't just big, it's big with secrets. This brings us to the next layer of the unknown, the true size of the universe, beyond our observable horizon. We've established that our observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is about 93 billion light years in diameter. But this is merely our light-limited horizon, not necessarily the edge of existence. If the universe is truly flat, as our observations of the cosmic microwave background suggest, then it is, by definition, infinite. Imagine that. Not just vast, not just enormous, but literally without end. How do you even begin to wrap your mind around infinity? It's a concept that defies human intuition, a number without a final digit. If the universe is infinite, then every single galaxy we've ever counted, every supercluster we've mapped, every cosmic void we've observed is but an infinitesimal speck within an unending expanse. It means that there could be endless repetitions of everything, galaxies identical to the Milky Way, planets just like Earth. Even you, reading these very words, living out countless versions of your life in distant, unknowable reaches of the cosmos. It's a dizzying thought, a conceptual vertigo that expands the mind to its breaking point. We gaze out at our observable bubble, aware that just beyond that cosmic horizon the universe continues, perhaps endlessly, perhaps with structures and phenomena we can't even begin to predict. Our 93 billion light-year sphere is just a tiny spotlight in an infinitely dark theatre. And if infinity wasn't enough to challenge your perception of everything, consider the multiverse hypothesis. This isn't just about our universe being infinite. It's about our universe being one of many. Imagine our entire universe, all 2 trillion galaxies, all she's dark matter and dark energy, all counts 93 billion light years of observable space and potentially infinite space beyond, as merely a single bubble in a vast, frothing ocean of other universes. The multiverse comes in many flavors, each more mind-bending than the last. There's the idea of an infinite universe, leading to infinite repetitions as mentioned. Then there's eternal inflation, where our universe is just one of countless bubble universes that have budded off from an eternally expanding inflationary space-time, each with potentially different physical laws, different constants, different fundamental forces. In one such universe, gravity might be stronger. In another, light might travel at a different speed. We are but one experiment in an infinite cosmic laboratory, or consider our brain worlds, where our universe is a brain, a higher dimensional membrane, floating in a larger, higher dimensional space, occasionally bumping into other brains, perhaps giving rise to new, big bangs. This isn't science fiction anymore. These are serious theoretical constructs being explored by physicists trying to reconcile quantum mechanics with general relativity. If the multiverse is real, then the question, how big is the universe, becomes almost trivial. It's not just big, it's part of something unimaginably, incomprehensibly more. Our universe, for all its majesty, might just be a single leaf on an infinite tree, a single grain of sand on an endless beach of existence. This radical shift in perspective inevitably leads us back to a question that has haunted thinkers for centuries. Are we alone? The Fermi paradox looms large here. If the universe is so vast, if there are potentially infinite universes, and if our galaxy alone contains hundreds of billions of stars, many with planets in habitable zones, then where is everyone? Why do we not detect the whispers of other civilizations, the grand designs of alien megastructures, the radio signals of beings who have also gazed up at their night sky and pondered their place? We've explored the immense scale that makes life probable elsewhere. We've seen that our Milky Way is a cosmic island, but one of a 2 trillion such islands within our observable reach. The numbers suggest life should be abundant, yet the silence is deafening. Is it because advanced civilizations are rare, destroying themselves before they can reach interstellar communication? Are they simply too far away, their signals lost in the vast cosmic ocean? Or is there a great filter, a barrier so difficult to overcome that very few species ever make it past a certain technological threshold? Perhaps an event that lies in our own future. The Fermi paradox is a stark reminder of our cosmic solitude, or perhaps our cosmic naivete. It forces us to confront the possibility that even in a universe of such staggering proportions, intelligent life might be an exceptionally rare, fragile phenomenon. Or perhaps we are simply not listening correctly, or they are too advanced for us to even recognize their presence. The sheer scale of the universe amplifies this paradox, making the silence all the more profound, all the more unsettling. You are a tiny speck on a tiny planet in a tiny solar system in one of billions of galaxies, and yet you might be part of the only consciousness capable of asking these questions in this entire observable realm. That is an awe-inspiring yet humbling thought. So where does this leave us? We've embarked on a journey that began with familiar scales and ended in the realm of the truly incomprehensible. We started by measuring light years and parsecs, and we've concluded with discussions of invisible forces, infinite expanses, and parallel realities. The universe is not just big, it is a tapestry woven from the known and the unknown, the seen and the unseen, the measurable and the profoundly mysterious. But this isn't a journey to despair or resignation. Quite the opposite. This is a journey to inspiration. It is a testament to the insatiable curiosity that burns within us, the tiny beings on a pale blue dot. Despite our cosmic insignificance, we possess the capacity to observe, to theorize, to build instruments that peer back to the very first moments of creation. We are the universe's way of knowing itself. Our telescopes are our extended eyes, our particle accelerators are probing fingers, our minds the crucible in which cosmic secrets are slowly, painstakingly forged into understanding. Every new discovery, every refined measurement, every theoretical breakthrough chips away at the wall of the unknown. We are not just passive observers, we are active participants in this cosmic narrative. The quest for what dark matter continues. The hunt for dark energies, true nature intensifies. Scientists are constantly pushing the boundaries of observation, searching for gravitational waves from the early universe that might hint at inflationary epochs and the existence of other universes. We are developing new methods to scan the heavens for signs of intelligent life, refining our search for those elusive signals. The universe, in its boundless majesty, continues to whisper its secrets, and we, with our limited senses and immense intellect, continue to listen. We are driven by an innate desire to understand our place, to unravel the grand designs, to comprehend the ultimate reality. The journey we've taken together, from our backyard to the edge of the observable cosmos and beyond, is not just about numbers and distances. It's about the human spirit, its boundless capacity for wonder, its relentless pursuit of knowledge, and its profound ability to find meaning in the face of overwhelming scale. The universe is immeasurably vast, incomprehensibly complex, and profoundly mysterious. But our capacity to think about it, to question it, to explore it, that perhaps is the greatest wonder of all. As we close this chapter, let us carry forward not just the facts of cosmic scale, but the awe, the humility, and the burning desire to continue looking up, to continue asking, and to continue reaching for the stars, for the next layer of understanding, for the next echo from the edge of knowing. The story of the universe is still being written, and we are, in our own small way, holding the pen. We've journeyed through the astounding scales of the universe, from our galactic neighbourhood to the farthest reaches of the observable cosmos, and even dared to glimpse the speculative realms of the multiverse. But as we stand at the precipice of this vastness, peering into the cosmic abyss, we encounter the truly profound questions, the known unknowns, that define our current understanding and ignite our deepest curiosity. These aren't just missing pieces of a puzzle, they are the very fabric of the universe, the dominant forces and phenomena that we know that exist, yet remain shrouded in mystery. They are the grand designs we are still striving to comprehend. Dark matter, dark energy, and the unsettling silence of the Fermi paradox. Imagine, if you will, that you are an archaeologist uncovering an ancient, magnificent city. You see the towering structures, the intricate carvings, the bustling marketplaces. But then you realise that 95% of the city's foundations, the very scaffolding that holds it all together, is invisible. You know it's there because the buildings stand, because the city functions, but you cannot see it, touch it, or understand what it's made of. This is precisely our predicament with dark matter and dark energy. Let's first confront the enigma of the dark matter. We've established that it makes up about 27% of the universe's total mass energy content. Think about that for a moment. Almost a third of everything that is out there remains utterly invisible and undetectable by any direct means. We can't see it, it doesn't emit or absorb light, it doesn't reflect light, and it doesn't interact with the electromagnetic force in any way we currently understand. So how do we even know it exists? This is where the universe reveals its secrets through its effects, like a phantom limb that still exerts a powerful grip. We infer dark matter's presence through its gravitational influence. We see galaxies rotating far too quickly for the visible matter within them to hold them together. Without the added gravitational pull of an invisible halo of dark matter, they would simply fly apart. We observe gravitational lensing, where the immense gravity of galaxy clusters warps space-time, bending the light from more distant galaxies like a cosmic magnifying glass. The amount of bending we see is far greater than what visible matter alone could produce, telling us there's a colossal amount of unseen mass at play. And when we map the large-scale structure of the cosmic web, those vast filaments and clusters of galaxies, we find that dark matter provides the essential gravitational scaffolding, the invisible framework upon which the visible universe is built. Without it, the universe as we know it, with its galaxies, stars and planets, simply wouldn't exist. It's the silent architect, the unseen glue that holds the cosmos together. But what is it? That, my friend, is one of the most profound questions in modern physics. Is it composed of exotic, as yet undiscovered particles like WIMPs, weakly interacting massive particles, or actions? Could it be primordial black holes formed in the early universe? Scientists around the globe are engaged in a relentless quest to identify dark matter. Deep underground laboratories, shielded from cosmic rays, house detectors hoping to catch a fleeting interaction with a dark matter particle. Particle accelerators like the Large Hadron Collider push the boundaries of energy, attempting to create these elusive particles in controlled collisions. Space telescopes meticulously map the cosmic microwave background and the distribution of galaxies, looking for subtle clues. Yet for all our ingenuity, dark matter continues to evade direct detection, a cosmic whisper that shapes everything but remains stubbornly silent to our instruments. It's a humbling thought, isn't it? That the vast majority of matter in the universe is fundamentally alien to our everyday experience, a ghost in the cosmic machine. And if dark matter is the invisible architect, then dark energy is the ghost in the machine's engine, the even more perplexing force that dominates the universe. Making up an astonishing 68% of the universe's total mass energy, dark energy is responsible for the universe's accelerating expansion. Think about that. 95% of everything that exists is beyond our direct comprehension. Our sun, our earth, our bodies, the very atoms we are made of, all of it comprises less than 5% of the universe. We are truly living in a cosmic enigma. The discovery of dark energy in the late 90s was a monumental shock. Scientists had expected the universe's expansion to be slowing down due to the gravitational pull of all the matter within it. Instead, observations of distant dwarf-type Ia supernovae, which act as standard candles for measuring cosmic distances, reveal the opposite. The expansion is speeding up. It's as if you threw a ball into the air expecting it to slow down and fall, but instead it started accelerating away from you faster and faster. This acceleration implies an unseen, repulsive force inherent to space itself, pushing everything apart. What is dark energy? This question is even more perplexing than dark matter. Is it a fundamental property of space, a cosmological constant, as Einstein once theorized, an intrinsic vacuum energy that constantly appears as new space is created? Or is it a dynamic, ever-changing field, a mysterious fluid dubbed quintessence, whose properties might evolve over cosmic time? The implications are staggering. The ultimate fate of the universe, whether it continues to expand indefinitely, eventually tearing itself apart in a big rip, or perhaps one day reverses course, hinges on the nature of dark energy. We observe its effects, we measure its relentless push, but its true identity remains one of the greatest unsolved mysteries in science, a cosmic riddle that dictates the very destiny of everything. These two dark components, dark matter and dark energy, represent our profound ignorance about the cosmos. They are not minor adjustments to our models, they are the dominant players, the very stage upon which the cosmic drama unfolds. We, with our visible matter and our fleeting lives, are but a footnote in a universe largely composed of the unseen and unknown. It's a humbling realization, a stark reminder of how much we still have to learn, and how much our current understanding of reality is based on a mere fraction of what is truly out there. But there's another profound mystery that isn't about the stuff of the universe, but rather about its inhabitants. This is the Fermi paradox, a question that has haunted scientists and philosophers for decades. If the universe is so vast, so ancient, and so teeming with stars and galaxies, why haven't we found any evidence of intelligent extraterrestrial life? Where is everybody? We've talked about the 2 trillion galaxies in the observable universe, each with hundreds of billions of stars. Many of these stars are orbited by planets, and we now know that rocky planets in the habitable zones of their stars are common. This sheer number suggests that life, even intelligent life, should be abundant. Given billions of years for life to evolve, for civilizations to rise and develop interstellar travel or communication, the galaxy should be buzzing with activity. We should see their megastructures, hear their signals, or find their probes. Yet, we detect nothing but silence. The cosmic radio waves are still, the night sky eerily quiet. This profound stillness leads us to the concept of the Great Filter. This idea suggests that somewhere along the path from the emergence of life to a highly advanced, interstellar travelling civilization, there is an extremely difficult, perhaps impossible step that almost all life fails to overcome. The Great Filter could be behind us, meaning humanity has already passed an incredibly rare and challenging evolutionary bottleneck. Perhaps the origin of life itself, abiogenesis, is extraordinarily improbable, or the evolution of complex cells or multicellularity or intelligence, or even the development of technology. If this is the case, then we are exceptionally lucky, and perhaps incredibly rare, a cosmic anomaly. This is the optimistic view, suggesting we are one of the few, if not the only species to have made it this far. However, the Great Filter could also be ahead of us. This is the more sobering, even terrifying possibility. It suggests that there is a hurdle that virtually all advanced civilizations inevitably encounter and fail to overcome. What could this be? It could be self-destruction through nuclear war, environmental collapse due to unchecked technological growth, the uncontrollable rise of artificial intelligence, a resource depletion crisis, or some other existential threat we haven't even conceived of yet. If the filter is ahead, then the silence we hear is a grim warning. Civilizations tend to disappear before they can spread across the stars. Every year we don't find evidence of alien life, the more ominous this possibility becomes, implying a bleak future for our own species. There are, of course, other explanations for the Fermi paradox. Perhaps intelligent life is incredibly rare and sparsely distributed, so far apart that we simply haven't had contact yet. Maybe they exist but are so fundamentally different from us that we wouldn't recognize their signs of life or communication. Perhaps they are deliberately hiding, following a zoo hypothesis, where they observe us without interfering, or a dark forest theory where civilizations remain silent to avoid attracting the attention of potentially hostile others. Or perhaps, and this is a possibility that always expands my own mind, they have advanced beyond our comprehension, transcending biological forms and operating on scales or in dimensions we cannot perceive. The Fermi paradox is not just a scientific puzzle, it's a mirror held up to humanity. It forces us to contemplate our own fragility, our place in the cosmic tapestry, and the potential pitfalls that lie ahead. Are we alone? Are we an exception? Or are we merely following a predictable path toward an inevitable silent end? The answers, if they ever come, will fundamentally reshape our understanding of life, intelligence, and our future. These three great mysteries, dark matter, dark energy, and the Fermi paradox, are the frontiers of our current knowledge. They are the driving forces behind countless hours of research, observation, and theoretical speculation. They remind us that for all our advancements, for all the incredible insights we've gained into the universe, the cosmos remains largely an enigma. We are still at the very beginning of our journey of understanding, constantly seeking answers to the unseen, the unknown, and the unimagined. Our capacity for curiosity, for scientific inquiry, and for wonder is, in a profound sense, the universe's way of understanding itself, an ongoing dialogue between the vast unknown and the small but determined minds that seek to unravel its grandest designs. We've traversed unimaginable distances, from the familiar comfort of our home planet to the sprawling tendrils of the cosmic web, and then out to the very edge of the observable universe, a sphere of 93 billion light years in diameter. We've even dared to peer beyond into the speculative realms of the multiverse. Yet as we stand at this precipice of cosmic understanding, the most profound questions aren't about how far, but how much and what. The universe, in its grand design, whispers secrets we are only just beginning to decipher, and some of its loudest whispers are about the things we cannot see. Remember the profound silence that echoes across the cosmos, the Fermi paradox, the unsettling lack of alien chatter, despite the staggering number of stars and galaxies. It leaves us with a chilling possibility. Perhaps we are truly alone, or perhaps the great filter lies ahead, a looming cosmic hurdle that intelligent life rarely, if ever, overcomes. This paradox, this cosmic quiet, amplifies the significance of our existence, our consciousness, our relentless drive to understand. We, this tiny speck of sentient matter on a pale blue dot, are the universe's way of observing itself, of asking its own questions. You, dear reader, are a part of that grand, unfolding inquiry. But the silence isn't just about other life. It's also about the vast, invisible majority of our universe. We've discovered that everything we can see, everything we can touch, taste and smell, the stars, the planets, the nebulae, you and I, accounts for less than 1% of the universe's total mass and energy. A staggering 25% remains hidden, a cosmic enigma shrouded in mystery. This isn't just a detail, it's the fundamental fabric of reality that we are only now beginning to grasp. The two titans of this cosmic unknown are dark matter and dark energy. They are not merely placeholders for our ignorance. They are active, dominant forces shaping the universe, yet they remain stubbornly beyond our direct observation. They are the unseen architects and drivers of everything we perceive. Let's first revisit dark matter. We know it's there because of its gravitational pull. We see galaxies spinning faster than they should, their outer stars holding on when they ought to be flung into the void. We see galaxy clusters, immense gravitational behemoths, bending light around them more powerfully than their visible matter could ever achieve. A phenomenon called gravitational lensing. We see the very structure of the cosmic web, those vast filaments and clusters of galaxies, held together by an invisible scaffold. All this evidence points to an unseen mass, a gravitational glue that constitutes about 27% of the universe's mass energy content. Imagine trying to understand the blueprint of a magnificent cathedral, but 85% of its materials are completely transparent. You see the stained glass windows, the stone arches, the intricate carvings, but the very walls and foundations that hold it all up are invisible. You can only infer their presence by how the visible parts are arranged, how they stand against gravity. That's our challenge with dark matter. It doesn't emit, absorb, or reflect light. It doesn't interact with the electromagnetic force, which means it doesn't interact with us in any way we currently understand except through gravity. It passes right through us, through our planet, through entire stars like a ghost. So how do we catch a ghost? Scientists are ingenious. We've built elaborate detectors deep underground, shielded from cosmic rays, hoping to catch a fleeting interaction between a dark matter particle and a regular atom. Experiments like Lux, Xenon, and Pandax are designed to detect WIMPs, weakly interacting massive particles, one of the leading candidates for dark matter. These detectors are essentially ultra-sensitive targets, often tanks of super-cooled liquid xenon or germanium crystals, waiting for an incredibly rare tap from a dark matter particle. It's like trying to hear a single raindrop fall in a hurricane, or feel a feather brush your skin while you're standing in a gale. The silence of these detectors, the lack of detection, is itself a profound piece of information narrowing down the possibilities. Other approaches include looking for annihilation products of dark matter, should it interact with itself, or searching for subtle changes in the orbits of stars in our own Milky Way, hoping to map out the invisible halo of dark matter that envelops our galaxy. The quest for dark matter is a global scientific endeavour, a testament to humanity's collective curiosity, pushing the boundaries of particle physics and astrophysics simultaneously. It's a hunt for something fundamental, something that could revolutionize our understanding of matter itself. What if dark matter isn't just one type of particle, but an entire dark sector of particles, forming a hidden mirror universe alongside our own? The possibilities are mind-bending. Then there is dark energy, an even more perplexing entity. It's the dominant force in the universe, making up approximately of its total mass energy. If dark matter is the invisible glue, dark energy is the invisible anti-gravity, the engine driving the universe's accelerating expansion. For most of the 20th century, scientists believed that the universe's expansion, initiated by the Big Bang, should be slowing down due to the collective gravity of all its matter. It was a logical assumption, but in the late 90s, observations of distant Type Ia supernovae, cosmic standard candles that allow us to measure vast distances, delivered a shocking revelation. The universe isn't just expanding, its expansion is speeding up. It's as if you threw a ball into the air expecting it to slow down and fall, but instead, it started accelerating away from you faster and faster. This accelerating expansion requires a source of repulsive gravity, a pervasive, mysterious energy inherent to space itself, dark energy. What is it? That's one of the biggest unanswered questions in all of science. One leading candidate is the cosmological constant, first proposed by Albert Einstein. He introduced it into his equations of general relativity to achieve a static universe, a universe he then called his biggest blunder after Edwin Hubble discovered the universe was expanding. Ironically, this blunder might turn out to be one of his greatest insights. The cosmological constant represents the energy density of empty space itself. As space expands, more empty space is created, and thus more dark energy driving further expansion. It's a self-sustaining engine. Another hypothesis is quintessence, a dynamic energy field that changes over time and space, similar to the Higgs field but with different properties. The nature of dark energy is not just an academic curiosity, it dictates the ultimate fate of the universe. Will it continue to expand forever, eventually leading to a cold, dark, big freeze or heat death, where all stars die out and galaxies drift infinitely apart? Or will the repulsive force grow so strong that it rips apart galaxies, stars, planets, and even atoms in a catastrophic big rip? The answer lies hidden within the nature of dark energy. The fascinating thing is how these two great unknowns, dark matter and dark energy, are inextricably linked to the universe's grand narrative. Dark matter provided the gravitational scaffolding for the first galaxies to form, shaping the cosmic web. Without it, visible matter would have been too diffuse to clump together into the structures we see today. Dark energy, on the other hand, began to dominate the universe's expansion roughly 5 or 6 billion years ago, slowing down the formation of new structures and pushing galaxies further apart. They are two sides of the same cosmic coin, their interplay defining the past, present, and future of everything. Our journey through the cosmos is far from over. In fact, in many ways, it's just beginning. The greatest discoveries often lie beyond the visible, beyond the familiar. We are building new observatories, like the upcoming Nancy Grace Ormond Space Telescope, designed to map dark energy and track the distribution of dark matter with unprecedented precision. We are developing new particle accelerators and gravitational wave detectors, like the proposed laser interferometer space antenna, hoping to catch the subtle ripples of space-time that might carry clues about the universe's darkest secrets. The universe, in its boundless generosity, continues to offer new frontiers for exploration. It challenges us, humbles us, and inspires us to push the boundaries of our knowledge. You might feel incredibly small contemplating these vast cosmic forces, these immense scales. But remember, you are part of the only known entity in this observable universe capable of asking these questions, of seeking these answers. Your mind, your curiosity, is a beacon in the cosmic dark. This constant pursuit of understanding, this insatiable hunger for truth, is what defines us. We are not just exploring the universe, we are exploring the very limits of our own comprehension. The answers to dark matter and dark energy will not just fill gaps in our physics textbooks, they will fundamentally alter our perception of reality, perhaps even revealing new dimensions or forces we cannot yet conceive. They will unveil the deepest secrets of creation and the ultimate destiny of all that is. The universe is not just big, it is profoundly mysterious, and we are its willing, eager detectives. Our adventure continues not just outward into space, but inward into the very essence of existence.